All right, let's get started. So, take a look at the exam. If there's problem with points don't add up, or the points, I don't know, just some. If you have problem with the points, let me know. I can fix it right now. But if it's a question about, you feel like the grading was not fair, or if you feel like you did the right work but the points were still taken, or if you feel like your work deserved 10 points but you only got 1, something like that, you should just write an email to Professor Gibson, ask to be regraded. When you send the email, make sure you also include a copy of your work. Just take a picture of it, attached to the email. Questions on that? Well, and also keep in mind that you have 4 exams. One of them will be dropped at the end. So if it's if for whatever reason you couldn't do your best on this exam, it's not the worst case. Any questions about the exam or the grading? I did not grade all the problems. I grade the first one. So if you have questions about the first one, we can talk about it. You still have to submit a regrading request after that. Okay? So I want to go through the first problem here because there was a few spots that you could make a mistake or someone else did. So we're solving this differential equation, and it tells you it's separable differential equation, so we're going to use separation of variables. We need to move the y function to the left and move dx to the other side. So if I do that, I get 1 over y squared dy equals cosine 2x dx. Then I'm going to integrate both sides, but before I do that, the left-hand side I'm going to write as y to the negative 2 dy. The right-hand side I'm going to leave it the way it is for now. When I integrate, the left-hand side is not going to be natural log, right? Because it's not 1 over y we integrate. It's y to the 1 over y squared. See if you can find what it's nice here. So that's just going to be adding 1 to the exponent, divided by the new exponent. The left-hand side will give us y to the negative 1, because we add 1 to negative 2. Then we're going to divide by negative 1, so that's a negative y to the negative 1. The right-hand side, when you integrate, you have to be a bit more careful, because it's 2x inside cosine. We can use u substitution. So let u equals 2x du equals 2 dx, and we need to replace the dx there, so we can write as 1/2 du equals dx. The right hand side becomes integral cosine u 1/2 du, so I'm going to put 1/2 outside, du stay inside. Now I can integrate the right hand side, which is 1/2. When we integrate cosine, we get positive sign. U is 2x plus c. Right, so we check if we take the derivative of sine, we get positive cosine. So when we integrate cosine, we get positive sine. So there was a few mistakes here, and a couple of mistakes when integrating cosine to x. The next step is about solving for y, so we can divide by negative 1 or multiply by negative 1, doesn't matter. So I get y to the negative 1 equals negative 1/2 sine 2x minus c, or you can write as plus the c1, the different c value. How do we solve for y? Well, the left-hand side, if you rewrite it as a fraction, is 1 over y equals negative 1/2 sine 2x minus c. We can find the reciprocal of both sides. Literally just flip both sides, right? So that's a y on the left and a 1 over negative 1/2 sine 2x minus c on the right side. You have to be careful. We added the c right after we integrate, So when we solve for y, your c should just stay with the sign. Over here, when we find the reciprocal, the c should be in the denominator, not on the side. So that's a general solution. You can rewrite it by multiply by -2 from numerator and denominator. You might end up with y equals -2 over sine 2x plus 2c, I think. Double check. You might call this c1, the c value, that's fine. So the next step is using the initial condition to find the c. So using y of 0 equals -1, put in there. So you get -1. It doesn't matter which one you use, right? I'm using the one on the left, but you probably prefer to use the one on the right. It doesn't matter. So -1 equals 1 over -1/2 sine 2 times 0 is 0 minus c is still in the denominator. Recall that sine of 0 is 0, it's not 1. Right? Cosine of 0 is 1, sine of 0 is 0. And it turns out that c equals 1 here. Then you can write down the actual solution. Not a lot. A couple of students found the c, but didn't put the c back into the general solution. It's a pity. So now what do? We need to find so after we find the solution, we need to find the solution interval. If we work from the solution form on the left, we really don't want the denominator to be 0, right? Same thing on the right. We want the denominator to be non-zero. So we just say -1/2 sine 2x minus 1 cannot equal to 0. Move the 1 over, multiply by -2. So we get sine 2x cannot equal to -2. If we take this denominator is the same, right? We just move the 2 to the other side. Okay, so for which x value is sine 2x not equal to 0? I mean, not equal to -2. Some of you was trying to, solve for x by finding inverse sine and then divide by 2. But if you go back to sine graph, so y equals sine x, and then you recall that for sine function, the highest value is +1, the lowest value is -1. Doesn't matter what x is, so it doesn't matter what goes into the sine, because the infinity, the answer is always going to be between +1 and -1. So because sine 2x or 3x or 5x squared, doesn't matter what it is inside, that is always going to be from +1 to -1, always. Therefore, the inequality we had, this one, that's going to be true for any x. That means for any x in as real numbers, any real number x. Any questions? So maybe that was the sort of the tricky part at the end. This part. But before that, there was a number of spots like finding the reciprocal to solve for y, or even integrating. There was a few mistakes. I'm not going to go through the second problem step by step. I just want to point out at the end when you find the solution interval. So number 2, so suppose we did everything correctly. At the end, we're going to end up with the general solution, y equals 2x squared plus c over x. This is the general solution. And then if we take the initial condition given, y of 1 equals 3, put in there, and then we can solve for c, which is 1, and then at the end, the specific solution is going to be 2x squared plus 1 over x. Perhaps you rewrite this as y equals 2x plus 1 over x, right? Either form is fine. When we want to find the solution interval, we have to be careful the denominator cannot equal to 0. So solution interval, we have to make sure that the x cannot equal to 0 in the denominator, which tell us, if you just look at a number line, it means that either to the left side of 0 or to the right. So we're going to have negative infinity to 0, or we're going to have 0 to positive infinity. That would be true, it's correct, if we look at the general solution, right? If we don't know what the initial condition is for the general solution, this will be correct. But the problem is that we want to know the solution interval for this specific solution we found. This solution is only valid for this x equal to 1. Right? So your solution interval must contain that x value 1. This is the correct interval here, and the one on the left, we don't use it here. So at the end of the correct solution interval, this second problem is from 0 to positive infinity. Because x equal to 1 is in here. Questions? Any comments about the exam? Was it fair? I would say like there's a lot, just kind of like if you think about back then when you take algebra classes, there's a lot of steps that you could make mistakes, even though you get the big picture right. You know how to do it. It's just that sometimes a small integration or maybe like the small, I don't know, small algebraic problems is going to kind of make your solution look weird at the end and lead to more problems. But what can I say? I didn't write the questions. Like I said, if you feel like your grading was not fair and you feel like you deserve more points, something like that, you should send a regrading request. Any other questions? All right. If you don't have questions, we can spend a few minutes to talk about the material that you talked about recently with the higher order linear constant coefficient homogeneous differential equations. It's a mouthful, but it's a type of equation that's very interesting to solve. So, let me just kind of copy down a few things from the professor's notes. So higher order linear constant coefficients homogeneous differential equations. It has the general form of a n y to the nth derivative, x being the input, plus a n minus 1 y to the n minus 1th derivative, and the derivative reduced by 1 each time. and then a2y second derivative plus a1y prime plus a0y of x equals 0. If you remember that for the order of the differential equation is given by the highest derivative. So this is the highest derivative, n. So n is the order number. So n is the order number. And usually when we talk about higher order, we talk about the second derivative, third, and the fourth derivative, and so on. But if it's a first order differential equation, it still fits this general form. So n could be greater or equal to 1. And it's linear in the sense that we don't have, it's in the sense that we only have the y and the derivatives, they all raise to the first power. So here we have y to the first power, y prime to the first power, y second prime to the first power. We only have power 1. We don't have nonlinear terms. Nonlinear terms like, for example, y squared. That's a nonlinear term. Or y prime times y, that's also nonlinear because it's a product of two linear terms. So we don't have any of this. That's good. And the constant coefficients is, we talk about a sub n minus 1, a2, a1, a0, those coefficients of y and the derivatives, they're all constants. And the homogeneous referred to the right-hand side is going to be 0 when you write in this form. I would say try to get comfortable with those terms, because in the future when you look at an equation, you know it's a linear, constant coefficient, homogeneous, and then you can basically follow the same approach to solve it. And to solving this equation, it's not like we take the equation and go from the top, the beginning, until we reach the final solution. It doesn't work like that. So to solve this, we're going to propose a solution on that, which is going to be y equals e to the lambda x. Doesn't matter what the n is, you can always begin with this solution and try to figure out what the lambda is and then come up with the final solution. So we take this, then we're going to put in there, so we need the derivative, the second derivative, and all the way to the nth derivative. And to put back in there, we end up with some kind of equation after we simplify. So that's a big picture. I'm not going to kind of talk too much on that part. So today we're just going to look at a few examples on second order linear constant coefficient homogeneous equations that look like some constant a, y double prime plus by prime plus cy equals 0. So again, it's linear because every term either have a y or one derivative of y. And all the coefficients a, b, c are constants. So that's a linear constant coefficient homogeneous. That's a 0. So how do we solve this? We begin with the ansatz. Same one, y equals e to the lambda x. We take this, we find the derivative, and then we put back into the differential equation and see if it works. And if it works, at some point we're going to end up with, this is what we call the characteristic equation. I'll show you with the example where this comes from. which allow us to solve for lambda, lambda 1, lambda 2, and after we find lambda, we can take them, plug in e to the lambda x to get the solution. Suppose lambda and the lambda 2 are different. So see that we were able to find the two base solutions. It turns out that any coefficient, any constant times this solution will be times e to the lambda 1x will also be a solution. Any constant times e to the lambda 2x is also a solution. And any combination means that if you add the multiples of each of them, it's also going to be a solution. So that's what we call the general solution, which is the linear combination of those two. So that's a y equals c1 e to the lambda 1x plus c2 e to the lambda 2 of x. And the c1, c2, they could be any number for the differential equation. But if we know initial conditions are given, then they might be different. But for now, those two could be any number. All right, with that said, let's look at a couple examples before you all fall asleep. All right, the first one I have is, let's see. We're going to solve the initial value problem, y double prime plus 11y prime plus 24y equals 0 with initial conditions, y of 0 equals 0, y prime of 0 equals -7. So we're not going to begin with the equation, we begin with what the solution looks like, the ansatz. And that practice, by taking some ansatz, put into the differential equation, try to solve for the ansatz, try to figure out what the ansatz is at the end. That's kind of the process in many differential equation examples. So here the ansatz is y equals e to the lambda x. For a different type of equation, we're going to use different ansatz, but for now, just remember this. Then we can figure out the derivative by using chain rule, right? So that will be e to the lambda x times lambda, and the y double prime is going to be, again, take the derivative, so that's a lambda times e to the lambda x times another lambda, so that's a lambda squared. Now we're going to put them into the differential equation. So we get lambda squared e to the lambda x plus 11 lambda e to the lambda x plus 24 e to the lambda x equals 0. Factor out the e to the lambda x. So we get e to the lambda x lambda squared plus 11 lambda plus 24 equals 0. So now we have a product. We have exponential term times this parentheses equals 0. That means one of them has to be 0. It could be either one. But then if you look at it, the exponential term, it's kind of like y equals e to the x, right? Or e to the negative x. It never goes to 0. It could be exponential decay or growth, but it's never equal to 0. It leaves us this parentheses part lambda squared plus 11 lambda plus 24 has to equal to 0. This is a very important equation. Because it tells us what the solution at the end will look like. We can solve for lambda here, so we get a, it's really just a quadratic equation, right? You can either use the quadratic formula or factoring, whichever you feel comfortable. So that will be lambda plus 3, lambda plus 8. Give us lambda 1 equals negative 3, lambda 2 equals negative 8. Those are distinct roots, which is a good thing. If we have the lambda value, then we can go back to the answer y equals e to the lambda x. We can plug in those values. If we use the first one, so we get y equals e to the negative 3x. If we plug in negative 8, we get y equals e to the negative 8x. You can check, it's actually both of them will work as a solution to the differential equation. It may not satisfy the initial conditions, but it definitely satisfies the differential equation. So we got those two we can use. This is what I would call base solutions. And any combination of them, so if we take one multiplied by a constant plus a constant times another one, the second one, that should also be the solution. That's the general solution. So we got y equals c1 e to the negative 3x plus c2 e to the negative 8x. So this is the general solution. In the future, if they say solve the differential equation, it doesn't give you initial condition, you should reach the general solution, not the two-phase solution. Any questions at this point? All right, so the next part is just about finding C1 and C2. So we have two unknowns at the end, and we happen to be given two initial conditions, right? And in fact, you do need to know two initial conditions to solve for the unknowns. So we're going to use them. So we're going to use initial condition y of 0 equals 0 to find C1 and C2, but we also need y prime of 0 equals negative 7. This one, we can just plug in 0 for x and 0 for y, that's fine. But the second initial condition is for the derivative. So this says x equals 0, the derivative of y equals negative 7. So we have to find the derivative of y here before we plug in this initial condition. Y prime equals, again, taking the derivative at this point, just using chain rule. So that's going to be, what is it? C1 e to the negative 3x, but then there will be a negative 3 coming from the exponent, and then plus C2 e to the negative 8x times negative 8. So I'm going to drop the plus sign. So now I'm going to plug in 0, 0 for the general solution. So I get 0 equals C1 e to the 0 plus C2 e to the 0, which is a 1. So that's a 1. This is a 1. So we have C1 plus C2 equals 0, basically. Then we can see C1 plus C2 equals 0. When we take negative 7, put in there, and put into the derivative, and x equals 0 there, so we get negative 7 equals negative 3c1 minus 8c2. That's the second equation. Negative 3c1 minus 8c2 equals negative 7. It probably has been a while, but I'm sure you remember how to solve this system of equations. Either substitution or elimination, whichever you feel comfortable with this particular example. So suppose I'm to solve this system. So let's say I'm going to use elimination. I want to get rid of C1, so I'm going to take the first equation, multiply by 3. So I get 3c1 plus 3c2 equals 0. This is the new equation I get. And I'm going to add it to the existing equation, the second one, so this will become 0 when I add those two, I get minus 5c2. When I add this side, I get negative 7. And I can solve for c2, which is 7 over 5. And then we can solve for c1 is negative 7 over 5. Don't forget to plug those values into the general solution, which is y equals negative 7 over 5 e to the negative 3x plus 7 over 5 e to the negative 8x. And we might be asked to find the solution interval. And it turns out that for exponential functions, right, it's just all real numbers. Even though we have a negative exponent, if we want to get rid of the negative exponent, we get 1 over e to the 8x. It doesn't matter, it never becomes a 0 in the denominator. So it's all real numbers. Any questions on this? All right, we got 15 minutes, so maybe I'll give you a couple more examples. Is that okay? All right, the next example I have is, so we're going to solve y double prime plus 14y prime plus 49y equals 0 with initial condition y of negative 4 equals negative 1, y derivative, y prime, negative 4 equals 5. So, to solve this, again, the process is the same. We're just going to say the solution ansatz. It's going to be y equals e to the lambda x. And we're going to take this, we don't know what lambda is, but we suppose that's a solution. We put it into the differential equation, but we need to know the derivative first. It's the same derivatives as we have used in the previous problem. So y prime is lambda e to the lambda x. Y double prime is lambda squared e to the lambda x, coming from the derivatives of y. So put in there, we have lambda squared e to the lambda x plus 14 lambda e to the lambda x plus 49 e to the lambda x equals 0. And then we can take out e to the lambda x and divide by e to the lambda x to both sides of the equation. That will be gone, and then we end up with lambda squared plus 14 lambda plus 49 equals 0. Which is the characteristic equation. And we can solve for lambda. If we try to factor this, it turns out that we get lambda plus 7 for both parts. So we get lambda plus 7 squared. And lambda equals negative 7. We only get one value here. You probably sometimes see the notation of lambda 1, 2 as subscript. equals negative 7. It just means that the first lambda value is negative 7, the second one is also negative 7. It's the same. Okay, so in this case, if we try to write down the base solution, by taking lambda put into the ansatz, so we get y equals e to the negative 7x. Right, we only get 1. There should be a second one. It turns out that you don't have to show the work to derive this. The second base solution, I'm going to call it y2, is just going to be x times e to the negative 7x. It's the first solution multiplied by this constant, this variable x. And if you want to do the work to derive it, let's just see we don't have this. We don't have this given. We just found out this is the only base solution by using the ansatz. What we could do is that we could try second ansatz, y equals some function u of x times e to the lambda x, with lambda being negative 7. And if we take this, put it into the differential equation, and at some point we get a function of u, the equation of u, and then that's what we can solve to get u equals x. But we don't have to do all that work. You can just memorize it. This is this case, when we only got one lambda value, this is what we call a repeated roots. There will be another case is that when we have imaginary roots, again the solution will be a little bit different. So from here we can write down the general solution. Which is going to be y equals the first base solution times c1, so c1 e to the negative 7x, plus the second one, so c2 x e to the negative 7x. And that we don't know what c1 and c2 are, but we can find them by using the initial condition, which I really don't want to find it. Is it okay if I skip that part? Just keep in mind that when we use the first initial condition, y of negative 4 equals negative 1, we can plug in x equals negative 4, y equals negative 1 directly in here. But when we use the second one, y prime of negative 4 equals 5, we have to find the derivative of y first before we use this condition. The two things I want to do next, one is I want to mention that, this is the case that when we have a quadratic characteristic equation and then we end up with repeated roots, right? But what if we have a problem that, for example, suppose instead of having a second order differential equation, we have a third order, like y triple prime plus y second prime, and so on. That might be coefficient that's incorrect there. Suppose we have something like this, equals 0. It's still linear, constant coefficient, homogeneous, right? And then we follow the same ansatz. And then we plug the derivative into the differential equation. We get the characteristic equation, probably lambda cubed, and something equals 0. And we solve this. Suppose we end up with lambda 1 equals lambda 2 equals lambda 3 equals some value lambda. Right? All three roots are the same. What about the base solution for the differential equation at the end? It's going to be very similar to what we had over here. So the first one is just going to be e to the lambda x, doesn't change. The second one is going to be x times e to the lambda x. What do you suppose the third one is? If you have all three roots are the same. Excellent. So it'll be x squared e to the lambda x. Good. So you just increase the power of the x by 1 if you have more repeated roots. And then you use all three of them. C1 and this plus C2 and that plus C3 and this equals y. Well, you probably wonder, what if we have two of them are the same? Well, suppose, not this case, suppose at the end we have lambda 1 equals lambda 2, but it's not equal to lambda 3. No problem. It's just that you're going to have e to the lambda 1x, x e to the, let me write it down. So the base solution is going to be y1 equals e to the lambda 1x, y2 equals x e to the lambda 1x, y3 is equal to e to the lambda 2x. That's it. Sorry, lambda 3, I don't know. Those two corresponding to the two lambda values are the same. This one corresponding to the third one is different from the other two. So this works for like pretty much all the orders of this type of differential equations. Any questions? Okay. That's one last example I want him to at least give it to you. So we're going to solve this differential equation, 16y double prime minus 40y prime plus 25y equals 0. So here we have a number in front of the y, the highest derivative here, which is perfectly fine. We don't have to change any strategy here. So a couple of things you could do. You could either divide by 16 to rewrite this as y double prime minus 40 over 16y prime plus 25 over 16y to make it look like what we had before, if that helps. Or you could just work with what we had here directly by applying the ansatz. So the ansatz doesn't change. Y equals e to the lambda x. And to find the derivative, second derivative, I'm just going to write down quickly. And then we can take them, put in there. It doesn't matter which one you plug those terms in. So if you put into the original differential equation, you get 16 lambda squared e to the lambda x minus 40 lambda e to the lambda x plus 25 e to the lambda x equals 0. So the characteristic equation is going to be 16 lambda squared minus 40 lambda plus 25 equals 0. It's still going to be a quadratic equation. You might have to kind of think a little bit harder when you factor it, but you can always try to use quadratic formula. If you don't like the way it is, or you can just divide by 16 to make it look like lambda squared minus 40 over 16. If you simplify, that's 5/2 lambda plus 25 over 16, so that's a 5 over 4 squared equals 0. You might find it easier to factor in this form. In fact, here we just have a perfect square. The same thing on the left side. It turns out that we just have lambda minus 5/4 for both of them. I'm almost done here, maybe 1 minute. So we get lambda at the end is equal to 5/4 for both lambda values. So we only get one value. So here this is a case of repeated roots. So the base solution is going to be the first one, y1 equals e to the 5/4x. What about the second one? That's going to come from the first one times x. So y2 equals x e to the 5/4x. And don't forget to write down the general solution, because that will be the solution for the differential equation. I guess one last comment is that when you work on those problems, it might seem to be so easy, but a lot of times you forget this x here when you write down the general solution at the end. So definitely be mindful, don't forget this x. All right, on that note, it's 5 o'clock, I should let you go. One thing, I'm not going to be here on Thursday and the next Tuesday, but someone else will cover for me. It's going to be either a Zoom form or in person. I'm not sure what it is, but definitely watch out for the announcements. And again, if you have questions about the exam, feel free to send a request. And take care. I'll see you next week. All right, take care. Yep, take care.